have 9 joules to begin with and 3 joules at the end. Is that a decrease? Yes, it is. So we see that both of them, as always, as with all systems, like to lower their potential energy. All seek lower potential energy. It's just that the plus charge seeks lower voltage and the minus charge seeks higher voltage. And we see that again. So let's make a sketch of what does the voltage in general look like for this. So I'll make a voltage graph versus R, and then I'll make a voltage graph versus some axis. So here's the way to think of it. Like this is the negative value minus infinity is close by, and then you climb out to 0. So the negative sign basically flips it. It looks like this. You climb out from negative values up to 0 when you're very far away. If we were, let's say, to set the origin here, it would look like this. We'd have a voltage depression, or what I call a voltage valley. So negative charges make voltage, quote unquote, valleys. They are depressions of negative values that climb out to 0. So I kind of like to imagine it like 0, voltage of 0, that's like sea level, right? That's kind of what's the situation when nothing is around. We take the reference of voltage being 0. If you then start to dot the landscape with different charges, positive charges make voltage hills. They raise the voltage value to positive values. And negative charges make depressions. They make valleys. They lower it from 0 downward to negative values. Okay? So we can once again make a sketch here. Positive charges like to roll off of hills. Well, they also like to roll into valleys. They're the downhill ones. So a positive charge would like to roll down into the valley, which really just means it's attracted to negative charges at the bottom of those valleys. You can draw it over here too if you want. There's that positive charge seeking lower voltage. It can roll off hills, roll into valleys, and likewise, negative charges, we find they like to climb hills. They also like to climb out of valleys. So negative charge would want to get out of there. It would want to climb out of the valley. That's because what's at the bottom of that valley? That's another negative charge it doesn't like. Okay? So that's the general gist here of the voltage picture. And please remember that all of this stuff has to ultimately make it so that opposites attract and like repel. It's yet another set of middlemen rules that make sure that that happens. All right? So again, positive charges make voltage hills, so other positive charges want to get off them. Negative charges want to climb them. Negative charges make voltage valleys. So positive charges try to roll into them, negative charges want to climb out of them. It's all just opposites attract, like repel. but it's extremely handy computationally to do it this way because we know that the energy picture makes things very easy. So now that we have all the rules in place, let's see how far we can get with an example that's very much like several of the problems on your homework, and you're going to find that this method is a lot easier than what you see on homework number 1. No vectors in sight, and that's ideal, right? No SOHCAHTOA business. Okay. So the general gist, are there any questions before I start sketching that out? Okay, so here's the general gist before I do it specifically. Let's say I had, I don't know, plus Q1, plus Q2, plus Q3. And since I'm labeling them with capital letters, you can pretty much assume that they are nailed down, and their whole purpose in the problem is to make the environment, form the environment in some way without themselves having to be affected. So if I were to look at some point P here, the kind of problems that you are doing in homework number 1, this is the force and field perspective. Well, you do stuff like this, right? You find E1, that's the contribution from charge 1. These are all positive charges, so they are all radially away from said charges. Might look like this. And of course, you have to do this annoying vector addition. Yes? All your SOHCAHTOA stuff, and maybe find, I don't know, let's just guess that the electric field points something like this. This is E net. So what do we use that for? Well, sometimes I just stop there and just ask you what the net electric field is, but ultimately in the real world, what you do is you drop a charge there, and then it can tell you the force on it, right? You could calculate what's the force, what's the acceleration. You could calculate the angle that it initially shoots off with, right? But you can't really chase the trajectory from there because the force and electric field are going to change the moment it moves, right? So this has advantages. You can calculate the initial force, the initial acceleration, the initial angle, but you can't chase the trajectory. Can't chase the trajectory. The one exception would be if the electric field is uniform. I gave you a couple of those on homework 1. You're lucky if you get that. So here's what we do with the energy voltage picture. You have those same 3 charges, plus Q1, plus Q2, plus Q3. You have some point P out here that you're interested in knowing about. And man, is this easy, because the voltage net at that location is just the sum of 3 numbers. There's no SOHCAHTOA. All 3 of those charges have contributed not a vector, but a scalar to this location. And all you have to do is add the 3 numbers. Now, don't get me wrong, it may be a list of positive and negative numbers. Positive charges will contribute positive voltage. These all happen to be positive, so they all will have the positive values contributed. Negative charges might contribute a negative voltage value, but I'm sure you can add up a list of numbers, even if it's a mix of positives and negatives, far easier than all your SOHCAHTOA stuff, because this is scalar addition, right? Scalar addition, the kind of addition you've been doing since kindergarten, is way easier than the vector addition of these 3 things. This is vector addition. Much more difficult. So, then, once you drop a charge there, you can immediately calculate what is the initial potential energy that it has, right? So you calculated that V net, and then you just multiply by the charge you put there, you have the initial potential energy. Now, I should mention, just for full disclosure, that that potential energy really belongs to the whole system. If everybody was free to move, they'd all carve their own chunk of kinetic energy out of that shared pot of potential energy. However, to make your life easy, I'm going to assume that these three are nailed down. And so the only charge that's able to do anything to get rid of potential energy of the system is that movable one. And so we assign the potential energy to that guy. Okay? So this is the potential energy of this charge. Okay, so the potential energy of the system is usually assigned to the movable charge, which can actually do something with it. It can turn that potential energy into kinetic energy. All right, well, here's the thing. What is the potential energy, or the voltage, made by all of these three very far away? So when you're really far away, R equals infinity. What's the voltage made by each one? 0, right? All three of these hills, you're way, way far away from them. You've returned back to voltage of 0. So PE final is 0. Now, how do I know that that charge actually made it there? Well, just look at it, right? Why a positive charge is going to repel from three other positive charges? So it's going to fly off and eventually get really far away. And if the potential energy is going to decrease, where did that energy go? It went to kinetic energy. So you can do one of your energy conservation problems. And you can actually find out how far away, how fast it's going when it's repelled really far away. It's very straightforward. Now, the one thing that you don't know is, did it fly off over here, or here, or here? Oftentimes you don't care, okay? So this would help us know which way it went. So it's not like this is the, the smoking gun here. We don't know which way it went off. We don't know the initial angle. We don't know how much time it might take to do things, because that's also unavailable. But we can say very easily how fast is it going when it gets there. Okay, so that's the energy picture's strength, right, is to talk about trading location for speed. When you go from one location to another, you lose potential energy and you will gain kinetic energy. Okay, so what I'm going to do next, if I have time, which I have about 7 minutes, I'm going to do a problem in this style. So I'm going to go ahead and put some charges down and then do this kind of energy problem. All right, let's see. Let's go over here. So I'm going to have a number line. And let's go ahead and put the two charges on this number line, plus Q1 minus Q2. I've labeled them both positive and negative. They're in fact the two charges I used before. So they're actually equal and opposite. I just labeled them 1 and 2 for purposes of identification, so I can refer to each one of them. So first, what I want to do is I want to sketch V versus X overall. So how does these two charges being in the neighborhood inform the landscape? Then I want to specifically calculate V at x equals negative 0.5, and x equals 0. And the reason why I'm going to calculate those 2 points specifically is I'm going to release an object with a charge plus 1 coulomb, mass of 1 kilogram at rest from the first point. And let me label these. I guess I'll call this A and B. I want to release it from rest from A and ask how fast is it going when it arrives at B. All right, so first, let's make a sketch of what voltage values we would see along the x-axis. This is a one-dimensional problem, so the second dimension just represents the value that would be present at each location. Oh, and I have to tell you where these things are located, don't I? This is at x equals minus 1 meter, and this is at x equals plus 1 meter. So I'm looking at this, and I know that I'm going to have a voltage hill centered on the plus charge and a voltage valley centered on the other one. So I might draw it like this. This is my negative 1 meter and plus 1 meter. And I can sketch those out. Here's my voltage hill. Due to the positive charge, it peaks, it spikes at the location of the charge and then dies off to 0 eventually. And then, of course, I'm going to center my valley on my negative charge. Looks like this. And of course, that climbs up from negative values and doesn't get to 0 until it's infinity. But what I have to remember is that B, seen on the axis, is actually going to be the sum of these two. It's the sum of the positive value that's always contributed by charge 1 and the negative value that's always contributed by charge 2. So let me sketch the net. The reason I drew these in dotted lines is, of course, I need to account for both for the overall. Well, very near, you can probably guess that each one dominates. But then, when you start to get into the region where you're significantly informed by both, this is what happens. So notice that the positive is being, value of 1 is being taken off by the negative value of the other. We get something like this. So what we get is a hill next to a valley. Okay? So that's V versus X. Even though the voltage would never go to 0 based on either one alone, the combination can. Okay? And in fact, I know for sure that the voltage actually goes to 0 at x equals 0. Now, why is it that the two exactly added to 0 at exactly in the middle? Is that just a coincidence? How did that happen?
They're the same distance.
Same distance from the same amount of charge, right? This is where you can use some of the analysis that you did in homework number 1. What if it was a big and small charge? Big hill, small valley. Well, if you have a big hill and a small valley, right? Big charge, small charge. If you want them to have equal influence and either add to a 0 voltage or be a 0 electric field, then you have to give the small one an advantage. You have a big charge and a small charge. What's the advantage you can give to the small charge? Be closer, exactly. So if you had a big hill, small valley, then the 0 point would be closer to the small charge. You got to give each of them an advantage if they're going to be equal and cancel. All right, so we've done this. We've even shown already that at point, I guess at point B, V net equals V1 plus V2 equals KQ1 over R1 plus KQ2 over R2. We put in our +1 nanocoulomb here, our -1 nanocoulomb here. And of course, when we're at point B, which is the origin, what R value are we away from each one? What's the distance I am away from both charges when I'm at the origin? 1 meter. So that we already showed that's going to be 0. At point A is of course on the negative x-axis. I guess I should label these A and B. A, I'm closer to the hill than the valley, so I'm going to get a positive contribution. Let's knock that out. What do I get? I get, just to expedite, how far am I away from charge 1 at point A? I'm at 0.5 meters away, right? And I am 1.5 meters away from the other one, right? Remember, just put in positive distances. So what you end up getting is, if I look this up real quick, what is that? That's a number. I think it's 12 volts, plus 12 volts. I can label that over here, should I wish to. Here, at x is -0.5 meters, my voltage is plus 12. So, just so I don't have to come back to this example next time, let's talk through part C. I'm going to drop a charge here at rest to be informed by this landscape. Which way is it going to move? Well, it's going to definitely go from A to B. Number of different reasons you could explain that. The most basic, positives and positives repel, and this positive is also attracted to the negative. Win-win situation. What's another reason? Well, positive charges like lower voltage. So we'll gladly roll off that hill. So here's the tricky part. Or here's where you have to fight your urge to. So we found that at point B, your voltage was 0, which means your potential energy is 0. So does that mean you stop because you have exhausted your stored energy? No. You will keep right on going, rolling off the hill into the valley. Because 0 potential energy in this system is not the end of the line. There are plenty of great negative values of potential energy which are even lower, even better, that you can achieve by, of course, going to the negative voltage over here. Okay, so positive charges seek lower voltage, and negative voltages are lower than 0. This thing will gladly keep going, and of course you can hopefully see that. Even if you released it at rest at point B, it wouldn't be happy there. It would still go to the right. It's repelled by this and attracted by this. If you released it here, it would say, get me to those lower negative values. Okay? So that's the kind of flavor. I think I've finished everything on your homework with the exception of maybe one very easy problem, so I'll pick that up next week.